Hello, Assalamu alaikum. Welcome to our video presentation. My name is Muhammad Abu Saeed. My metric number 59409. So this video will cover state machine, state diagram, and state table. Okay, before we go through, let's know about what is state machine. Okay, state machine refers to a circuit that sequences through a set of predetermined states and controlled by a clock and other input signal. When we say the state machine is a sequential circuit, we already know the counter also a sequential circuit that have a regular numeric count sequences. So what is the differences between counter and state machine? Okay, the major differences between counter and state machine: counter is commonly used to count events. On the other hand, state machine is commonly used to control events. That's the main differences between counter and state machine. Okay, there are two models to describe for a sequential circuit: Mealy model and Moore model. What is Mealy model? Mealy model output signal are also controlled by additional input signals. In the Mealy model, output signals controlled by additional input signals. But in the Moore model, output signals doesn't have any external controls. Okay. In the Mealy model, output can change asynchronously. On the other hand, in the Moore model, output is a function only of the current flip-flop states. That's the differences between two models, Mealy models and Moore models. Now I will explain how to construct the state diagram and state transition table, and then how to design the sequential logic circuit to realize the output. Okay, before construct the state diagram, we need to understand the state table here. Okay, this is the present state, input, next state, and output. Okay, so we'll assume S0 equal to 0 and S1 equal to 1. Okay, S0 equal to 0, S1 equal to 1. Okay, so let's see in the first input. Present state 0, next state also 0. So present state 0, next state also the 0, like this. Okay, for the 0 present state, what is the input? Input is 0, output also the 0. So we write here 0 input and output also 0. Okay, let's see the second input. Present state 0, next state 1. So present state 0, next state 1. So present state 0, next state 1. This will going to the next state. For that, input is 1, output is 0. So input is 1, output is 0. Okay, and then for the third row, present state 1, and then next state also 1. Present state 1, next state also 1. And then input 0, output 0. Input 0, output 0. Last one, 1, 0. 1, 0. And then input 1, output also 1. Input 1, output also 1. That's the state diagram. You can see same one. Okay, let's see how to construct the state transition table based on KML. Okay. So our input is 2 here. Okay, this is next state Q and this is input. So 0 1 0 1. So okay, you see 2 1 here. So for this next state 1, for this one, what's the present state? 0 1. Okay, 0 1 1 here, and for this one 1 0 1 0 1 0. So 1 is here. So rest of the next state 0. So 0 0. So we can see this is the diagonal. So we already know for the diagonal n plus 1 equal to Qn bar x plus Qn x bar. We can write this Qn XOR x. Okay, for the output, this is the set present state, this is input 0 1 0 1. Okay, if you see in the output row only 1 here, so for this output present state 1 input is 1, so present state 1 input is 1. So what is that here? Okay, rest of the output is 0, so it will be 0. So only 1 here, only 1. So output will be y equal to Qn x. Qn x. Okay, now we will see how to design the sequential logic circuit based on these two equation here that we found from KML. We will design the sequential logic circuit based on the D flip-flop. So let's draw the D flip-flop first. Okay, Qn plus 1 Q bar. This is D. This is Qn. Okay, we can clearly see here 2 gates here. So this is OR gate and XOR gate. So This is our OR gate, this is our XOR gate. True input Qn XOR X. So Qn will connect and XOR X. So this is our X input. Okay. The output will be Qn plus 1. So our output Qn plus 1. And then y equal to Qn X. This is our Qn. So we just simply connect to this. And then X, this is our X. So this is our output y equal to Qn X. That's the logic circuit based on the flip-flop. Thank you.
So today I'm going to talk about state table and diagram. So as you can see, here is state A, state B, C and D. So for state A, if it is 0, if the value is 0, it will be here. If the value of A is 1, so it will go to state B. So for for state B, if it is 0, it will go back to A. If the value is 1, it will go to C. So for C, if the value is 0, it will go back to A. If the value is 1, it will go to D. So here, as you can see, for state D, if it is 1, so it go back to 1 because D over 1, because it is the state diagram, it is like this. And if it's 0, it will go back to A. So there are 4 states, which is state A, B and C, also D. So as I mentioned earlier, there are 4 states, which are A, B, C and D. So the number here, 0 and 1, here is the input. So we consider it as input X. Input X. So whereas the output, the number here, the denominator 0001, so output is we consider it as Z. So I make the tables here which have 4 states, which is A, B, C and D. So together with this, I draw the next state table which have X is equal to 0 and X is equal to 1. So for this table, we have to refer to this state diagram. So to complete this table, if for state A, if X is equal to 0, so where it goes, it will stay at A. So if it's 1, so it will go to B. So for state B, if it's 0, it will goes to A. If it is 1, it will go to C. So for state C, if it is 0, it will go to A. If it is 1, it will go to D. So for state D, if it is 1, it will stays at D. If it is 0, it will go to A. Just this next state, it depends on the state diagram that we have up here. So it will affect the configurations that we have inside here. So for the output, we just refer, as usual, we have to refer to the state diagram up here. So this over the denominator for each of every states is the output of every state. So for example, for state A, the output is 0. So for state B, the output is 0. So for state C, the output is 0 also. Whereas for state D, the output is 1. So basically we have finished with a state table, also with state diagram. First thing first, we have to do the state diagram first and figure out the input and output of every state. So we have to from that we will enable to do the state table. So as you can see from my previous lecture, so you can see that there are many ways that we can do to figure out the input and output of this state table and state diagram. So we will proceed to the next one. So we proceed with 3 states example. So the notation is input / output. So there are 3 states here, which are A, B, and C. So if my input for A is 0, the output is 0. For A, if the input is 1, the output is 0. It will go to B. So for state B, if the input is 0, the output is also 0, so it goes to A. So for input B, when the input is 1, so the output is 0, so it goes to C. So for this C, when the input is 1, the output is also 1. Whereas when the input is 0, the output is also will be 0, so it goes to A. So we will proceed to the state diagram. So again, I make the table here, the state table. For this one, it differs from the previous one that I did. So for the current state A, B, and C, there would be a next state, and I divided the next state to 2 parts, which is 0 and 1. Also for the output Z, I divided it into 0 and 1. So to understand this more, so we refer to the state diagram here. So for current state, for state A, so we refer here. So when the input is 0, it will stay. The output will be 0, right? So it will stays at A. Yes. So the output is 0. Okay. So if the input is 1, it will goes to B. Here you can see here the input is, if the input is 1, it will goes to B, whereas the output will be 0. Okay, so we proceed with state B. When for the next state, for this one, we focus on this one. When the input is 0, it will goes to A. Okay, so the output is 0. So if the input is 1, it will goes to C, so it will be 0. Okay, so for C, if the input is 1, so it stays at C, so it will be C here. So this is 1, because the output is 1. So if it is 0, it will goes to A, the output is 0. Okay.
Hello everyone, today we are going to talk about the various type of flip-flops in the state diagrams. There are 4 types of flip-flops in the state diagrams, which is the SR flip-flops, the JK flip-flops, D flip-flops, then T flip-flops. This type of flip-flop, as you can see from the table, then all 4 flip-flops have the same number of states and transitions. Each flip-flop is in the set state when Q is equal to 1. When Q is equal to 1, each SR, JK, and D and T flip-flops are in the set state. Meanwhile, the flip-flops will be in the reset state when they are in 0, when Q is equal to the 0. This can be seen from SR, JK, D, and T flip-flops. Also, each flip-flop can move from one state to another. Or it can enter the same state. The only difference between these 4 types of flip-flops lies between the values of the input signal that can cause transitions. In conclusion, a state diagram is a very convenient way to visualize the operations of flip-flops or even large sequential components. That's all for me. Thank you.